I would like to do a couple examples where I emphasize the interpretation of the partial derivative. So we'll start with a production function. The production of widgets in thousands will be given by P of LK, which is equal to 2 times L to the 0.6, K to the 0.4. L is going to be the cost of labor, and K is the capital costs, both of which are going to be given in thousands of dollars. So what we would like to understand using partial derivatives is if you change your labor costs by a little bit, or you change your capital costs by a little bit, how does that affect the total production of widgets? So if the company has labor costs of $100,000 and capital costs of $200,000, how many widgets are going to be produced? So essentially, what is P of 100, 200? So we're going to plug that into our function, 2 times 100 to the 0.6 times 200 to the 0.4. And that's going to give me 263.901, but the units here are in thousands of widgets. So that's 263,901 widgets that can be produced using $100,000 for labor costs and $200,000 for capital costs. Now I want to understand what happens when we change those costs, so I'm going to find the partial derivatives. So here, first I'm going to find the partial derivative of P with respect to L. So I have 2L to the 0.6. I'm going to bring that 0.6 down, so I get 1.2 L, and then 0.6 minus 1 is negative 0.4. And then I'm going to have K to the 0.4 because I'm taking the derivative with respect to L, so K is constant. So it just continues to multiply that expression. Now, what about the derivative of P with respect to K? So now L is constant, so 2 times L to the 0.6, that's constant. And then I have K to the 0.4. So I'm going to bring that 0.4 down. That's going to give me a 0.8 L to the 0.6. And then K to the 0.4 minus 1, that's negative 0.6. Okay, so these are my partial derivatives with respect to L and K. And now what I'd like to do is I would like to interpret those partial derivatives. So let's start with the partial derivative with respect to L at 100 and 200. So what is 1.2 times 100 to the negative 0.4 times 200 to the 0.4? Well, that equals 1.583. And now what does that mean? Well, that means that if our capital costs are constant, so if capital costs are fixed at $200,000, and then we're going to change our labor costs. And I find it's helpful to interpret derivatives in terms of a 1 unit change when looking at the variable that we're taking the derivative with respect to. So in this case, labor costs, I'm going to think about what happens when I increase those by 1 unit. So labor costs are increased from $100,000 to $101,000. Well, what is that going to do to production? Well, the partial derivative says production will increase by 1.583 thousand widgets. or in other words, 1,583 widgets. Okay, what happens if we increase our capital costs? In this sense, we need to plug in 100 and 200 to my partial derivative of p with respect to k. That's going to give me 0.8 times 100 to the 0.6 times 200 to the negative 0.6. Okay, that's going to be 0.528 if we put that into a calculator. So what does that mean? Well, in this case, capital costs are the variable, so labor costs are going to be fixed. So if labor costs are fixed, and in this case, $100,000, and then capital costs are increased from $200,000 to $201,000, again reflecting a 1 unit increase. Production will increase by, in this case, 0.528 thousand widgets. Or 528 widgets. So as you can see, in this model, if you increase your labor costs, then you get a larger production for each $1,000 that you invest in labor costs than you would if you had invested in capital costs. And so these partial derivatives give you a sense of if you have extra money, so now instead of having $300,000, maybe you have $350,000, they give you a sense of how you could allocate your budget best so that you can increase your production of widgets. In this case, it seems it's better to put more money into the labor costs than the capital costs. Okay, let's do one more example. This example has to do with the ideal gas law. You'll recall that the ideal gas law was that PV equals nRT, and we're going to look at the volume of 1 mole, and R in this case is going to be 0.082, and so what we can do is we can solve for volume. So we get that volume is given by, it's a function of temperature and pressure, and it's given by 0.082 times T over P, where P is pressure and T is temperature. So now I want to, first of all, just find what's the volume if my temperature is 300 Kelvin and my pressure is 2 atmospheres. So my units for pressure are going to be atmospheres, and my units for temperature are going to be Kelvin. That's so that my volume will be measured in meters cubed. So here, what is V of 302 for this gas? Okay, so that's 0.082 times 300 divided by 2. That's going to give me 12.3. Okay, so the volume of the gas at 300 Kelvin and 2 atmospheres of pressure is 12.3 meters cubed. Okay. Now we want to find all partial derivatives of volume as a function of temperature and pressure. So we want to understand what happens when you change the temperature by a little bit and what happens when you change the pressure by a little bit. Okay, so what is dV dt? Well, pressure in this case is a constant. I know we've got a division going on here, right? But pressure is a constant. So that means essentially that this function can be thought of as being 0.082 over P, a constant times temperature. And so the derivative of a constant times T is just going to be the constant. So it's going to be 0.082 divided by P. Now I want to find the derivative of volume with respect to pressure. So now pressure is going to be the variable. So here the constant is going to be 0.082 times T. And then that's going to be times, I'm going to call it P to the minus 1, so it's easier to take the derivative. Okay, so that's going to be a minus 0.082 T times P to the negative 2. P to the negative 2, another way to write that is 1 over P squared. So this is negative 0.082 T divided by P squared. And I want you to note something about these two derivatives. The first derivative is positive. That says if we increase the temperature, that's going to increase the volume of the gas, because pressure we're going to assume is positive. And then assuming, of course, temperature is positive, since we're measuring it in Kelvin, it will be positive, and that we have a P squared on the bottom, then if you increase the pressure, that should decrease the volume. And that makes sense, of course, because pressure is in the bottom of this expression. So if I increase pressure, then I'm going to divide by a larger number, so that should decrease the volume. Okay, so let's interpret again. Okay, first of all, let's find dV dt when we have a temperature of 300 Kelvin and we have 2 atmospheres of pressure. Okay, so that's going to be 0.082 over, in this case, P, which is 2. So that's 0.041. Okay, and now we want to interpret that. So here, pressure is constant. So if pressure is fixed at 2 atmospheres, an increase in temperature. Let's find out what happens, say, if you increase temperature by 1 unit. An increase in temperature from 300 Kelvin to 301 Kelvin. What's that going to do? That's going to increase the volume by a small amount. We'll increase volume. We could say by 0.041 meters cubed, but we could also say it could increase from 12.3 meters cubed to 12.341 meters cubed. So changing the temperature by 1 degree Kelvin is going to increase the volume of that ideal gas by just a little bit. Now, what about pressure? Okay, so the derivative of volume with respect to pressure, that's going to be negative 0.082 times my temperature of 300 kelvins divided by 2 atmospheres squared. And if we work that out, that's going to be negative 6.15. Okay. So if, in this case now, temperature is going to be held constant, at 300 Kelvin, an increase in pressure, and we're going to increase pressure from 2 to 3 atmospheres, because that's going to be a 1 unit change. Will decrease, in this case, because the rate of change is negative. Volume, let's see, we're going to take 12.3 meters cubed, and then we're going to subtract 6.15. When we do that, that will actually bring it down to 6.15 meters cubed. So if I increase the pressure from 2 to 3 atmospheres, that's going to decrease the volume. We expected that because the derivative was negative, but it's going to decrease it quite significantly from 12.3 meters cubed to 6.15 meters cubed. Okay, and that's the effect of what the units are in this case. 1 atmosphere is quite a lot of pressure. And so a change in pressure of 1 atmosphere in this case would be more significant than the change in temperature of 1 Kelvin. Okay, I made the numbers simple for this problem, and so I measured the pressure in terms of atmospheres. Usually pressure is going to be measured in something like pascals or kilopascals, but I decided to go with atmospheres just because it was going to be a little bit easier for us to do the computations. So now you can see what the effect is of increasing temperature for an ideal gas and increasing pressure and how that affects the volume.